Here's my suggested process for doing related rates problems with paper and pencil. Step 1, draw a picture. That's pretty much always my step 1. And make it mathematical. Give things and positions and distances variable names. Then write down the names and values that we already know. Then write down the name of what we want to know. Of course, we can't write down its value yet because we don't know it yet. Then write a formula or equation that describes the situation, but don't plug in the stuff we know from step 2 yet. Then find a rate by taking derivative on both sides. Usually this needs implicit differentiation, and that usually involves the chain rule. So in some sense, if you're doing a related rates problem and you haven't used the chain rule, you should probably go back and check what's going on. And then step 6, you change the derivative you get here, solve for the variable you want. The variable you want was listed up here to remind you. And then plug in your values from step 2 and do an actual computation. And it's important here that you haven't plugged in your variable values yet before you take the derivative, because once they're constants, then their derivatives are just 0 and life isn't interesting anymore. So let's try this on the bike problem. So step 1, draw a picture. We've already done this, but we might as well do it again. It helps if the picture's kind of to scale, but it doesn't have to be. We said that this was y, this was x. We had something moving this way at a rate dx dt. We had something moving this way at a rate dy dt. And we had h, and that was a right angle. Step 2, write down the names and values that we know. We know that y was 10 meters, x was 40 meters, dy dt was 4 meters per second, dx dt was negative 9 meters per second, and then we had h. We didn't know that off the top of our heads, but we could compute it, right? That was root x squared plus y squared. And you could compute that. It's not essential to compute it right now. Step 3, what do we want to know? We said, given how fast the bike is moving along the road, what's the rate of change of the distance that the radar observes? So that was dh dt. Step 4, write a formula or equation for the situation, but don't plug in the values we know yet. We actually just wrote that here. H equals root x squared plus y squared. And then step 5, find the rate of change of h by taking a derivative. So we might start and say dh dt equals ddt of this big old square root. You can imagine that's going to get a little ugly. We're going to have to do a half power and then a negative half, and then we're going to have to do the chain rule inside it. So let's just say that gets ugly. It's not impossible, but there's a more elegant way. Another way to think of the hypotenuse is to just say, well, h squared is x squared plus y squared, just squaring both sides of that formula, right? So now, how about taking the derivative? So we'll say ddt of h squared equals ddt of this whole thing. And we're doing implicit differentiation here. What's the derivative of h squared with respect to t? Well, if it was ddh of h squared, it would be 2h. So we can say that, but it's not ddt of h squared, ddh of h squared is ddt. So we have a chain rule term here. And then what's ddt of x squared? Same logic, it's 2x dx dt. And the same logic for y, 2y dy dt. And now, step 6, solve the results of step 5 for what we want. Let's just remind ourselves, we want dh dt. So what can we do with this to get dH/dt all by itself, divide both sides by 2h. And we'll get dH/dt equals, you could write it this way just to kind of save room, 1 over 2h times all that stuff, 2x dx dt plus 2y dy dt. And then plug in the known values from step 3, from step 2. So we can say dh dt equals 1 over 2h. We never actually calculated h up here. It was 41 something. So we'll just say 41-ish. Change this to 41-ish. Of course, you would be more careful with that than that, but we don't want to slow down the video here. And then 2, and what was x? It was 40 meters. And what was dx dt? It was negative 9 meters per second. Plus 2 times y. Y was 4, y was 10 meters. And dy dt was 4 meters per second. This 41-ish was meters. So do all the units work out here? That's a good question before we actually go doing any more arithmetic. We have meters times meters divided by seconds. Meters times meters divided by seconds. So we have meters squared per second here, which is kind of weird. That sounds like area. But then here we're going to divide by meters, so then we get meters per second. And dH/dt should be in meters per second. So all the units work out. We're okay to go do arithmetic. Now I strongly suggest you not doing arithmetic by hand on this. Just type this whole expression into a calculator all at once, or Desmos or something. So we'll say use calculator or Desmos. So let's go do that and see what we get. Actually, before we do that, I discovered a minor error here. This 10 should actually be minus 10. That would make a difference, huh? All right, now let's switch to Desmos. All right, I'm trying to be elegant here. In Desmos, I could have just said x equals 40, but then Desmos would draw a vertical line at 40. I could have said just y equals negative 10, but then it would have drawn a horizontal line at y equals negative 10. So if I give them names, then it won't draw confusing things on the graph. And I couldn't think of a way to do like dx dt or dy dt, so I just called it velocity bike, velocity car, and we just have to remember which way things are going. Then we tell it how to compute h. That was 41-ish, like I said. And then we can say how fast is h changing, and type in the formula we got, and we get negative 9.7. And compare that to our spreadsheet where we got negative 9.69. You could say, well, maybe I should have taken a smaller time step to get an answer that's more like negative 9.7, which is true in a pure math way of thinking, but in a real world situation, there's plus or minus probably 5% error at least in any radar measurement, at least at the commercial level. So I'd say our spreadsheet gave us basically the right answer even at 0.1 time step size. And it's kind of interesting, we used Desmos just as a calculator and didn't draw anything. Also notice that I didn't simplify by canceling the 2 here with the 2 there and the 2 there. That's just an extra step. It would have taken more time, it would have been error prone. So I like to leave equations basically as I find them. Here's another great way to think of it. You can say, where is the bike at time t? That's its initial position, which I guess I should have called x bike 0 for where it is at time 0, times the bike velocity time, plus the bike velocity times how much time has gone by. Same thing for what's the y position of the car? It's the it's the initial position of the car plus the car vertical velocity times t. Then we can say how long is the hypotenuse as a function of t, and that's just x squared plus y squared at the current time, whatever the current time is. And then we can ask the Desmos to take the derivative, the prime, and it'll graph that, and that's the function we saw in Excel. This purple curve, we also saw something like that in Excel. Notice I'm not graphing these. They're kind of confusing because one is in the x direction, one's in the y direction. Even though I had graphed them in Excel, I probably shouldn't have. And so that's the rate of change of the hypotenuse as we're going, and then we can also ask what's the derivative of the hypotenuse function at time 0, and we get that negative 9.70 something. So that's another great way to see it.